So let's look at one last problem in this section, and that's a logistic model. So this logistic model deals with an exponential, but you'll notice that this exponential expression, my variable, my independent variable x, or in this case t, is in the denominator. So we have an exponential and a rational expression combined. This gives us what we call our logistic model. And when we start dealing with rational expressions, we need to remember that they may have vertical, horizontal, or oblique asymptotes. All right, so let's look at this problem. The spread of an epidemic. I can't think of a more appropriate problem for us to be doing during our COVID-19 departure from school. So let's look at this spread of an epidemic. In a town whose initial population is 3,500 people, a disease creates an epidemic. The number of people, capital N, infected T days after the disease has begun is given by this logistic model function. N of T equals 3,500, that initial population, divided by the quantity 1 plus 19.9 E raised to the negative 0.6 T, so to the 6/10 of T, negative. So the first thing we might want to do would be to graph the function. We want to understand what this looks like. So you have to be careful typing this in your calculator when you go to graph this and you type it in your Y1 on your TI, that you get all of that denominator collected correctly. So I'm going to take my 3,500 and I will have that divided by the quantity 1 plus 19.9 E, and we're going to make sure all of negative 0.6 X remains in that exponent. And once you've typed it in, you're going to need to find the graph on your screen. One option is to hit zoom and then 0, and that will fit the graph. That's going to help you get it where you want to see it. But, you might want to change your window, right? So we change our window, which lets us know how to set our X min and X max and our Y min and Y max. And if I change my window, I'm going to look at X equals 0, or T in this case, time, 0 to 30. We're measuring days in this problem, right? So this is telling us T days. And there are only 3,500 people in the town. Is it possible for more than 3,500 people to become infected? And the answer is no, right? So maybe I'll set this at 4,000 because it's a little bit above 3,500. So that's my N on the Y-axis. And graphing this, you're going to get something that looks like this. This is what we call our logistic model, and it looks like it has a horizontal asymptote. Okay? Now, it's all relative how you set your window up. I just encourage you to think about, what is being considered, what your variables are. So we're talking about days, maybe 365 days, maybe 30 days, roughly a month. And then there were only 3,500 people, so I went from 0 to 4,000. And if I were changing my window, my X min would equal 0, and my X max would be 30. My Y min would be 0, and my Y max is 4,000. Okay, and I know I'm going to keep 0 for my X min and Y min because I can't have negative time and I can't have negative people. Okay, so this is what our function looks like. If I asked you how many people are initially infected with the disease, you would say, well, that would be on day 0 when the outbreak occurred. How many people? So that's going to involve, for part B, we're going to plug in 0 to our function. So for B here, n of 0 is 3,500 over 1 plus 19.9 e to the negative 0.6 times 0. So that's going to become e to the 0th power, and e to the 0th power is just going to be 1. So I end up here with 3,500 over 20.9. And evaluating that in my calculator, I get 167.46. So what this tells us is that on the very first day when this disease was exposed to the public, on the initial day, 168 people were initially infected. And even though logically or mathematically we should round that to 167, I'm going to round up because you can't have part of a person infected. All right, so find the number of people infected after 2 days, 5 days, 8 days, 12 days, and 16 days. So doing this, I'm going to do the exact same thing. I'm just going to plug in different values for my t. So I'm going to pause and write that out. So I encourage you to pause the video as well and make sure you can plug these values into your calculator and get the same outputs that I'm getting. So what we see here, if I evaluate the logistic model that we have for n at t equals 2, t equals 5, t equals 8, t equals 12, and t equals 16, we get these values. So initially, 168 people were infected. And after 2 days, that number has more than doubled to 500. Add 3 more days, that number has more than tripled. But at a certain point, the number is going to stop going up so rapidly. Why does that happen? Well, there's less people to infect, right? So it's still spreading. But by the time we get to 3,000 people, there are only 500 people left to infect. So it's not going to keep skyrocketing like it initially was. So you see that it starts to approach that number 3,500. So if we use this model, part D, and consider that, can we say whether all 3,500 people will ever be infected? Well, mathematically, we're going to get to some number. Say if I plug in n equals 30. If I plug in 30, my output value is going to give me number something 3499.998939. And so this number would certainly round to 3,500, right? So we would say, yeah, probably everyone's going to be infected. Mathematically, is that line ever going to touch, that logistic function ever going to touch my model here, which has a horizontal asymptote at y equals 3,500? We know mathematically it's always going to be below that, but at a certain point it's so close we just round it up. So this is why it is important that we are staying home, and we do stay home to social distance ourselves when things like this happen currently and in the future for some of you who might be watching this later.